plane passing through three non-collinear points. In this module, you will learn about the equation of a plane passing through three non-collinear points. If you are given three collinear points, can you guess how many planes will contain them? There will be many planes containing these three collinear points. Now, think about three non-collinear points and how many planes they determine. One and only one plane can be drawn through three non-collinear points. Therefore, you can say three given non-collinear points specify a particular plane. Consider a plane such that R, S and T are three non-collinear points on it. Let us assume that position vector of point R is vector A, position vector of point S is vector B, and position vector of point T is vector C. Since you know points R, S and T lie on the plane, you also know that vectors RS and RT will also lie on the same plane. The vector representing the cross product of vectors RS and RT is perpendicular to the plane containing vectors RS and RT. Now, consider any point P on the plane whose position vector is vector R. Now, you see that vector joining points R and P is represented by vector RP. Since vector RS cross RT is perpendicular to the plane, therefore, it is also perpendicular to every vector lying on the plane. Now you get the dot product of vectors RP and RS cross RT as 0 because the value of cosine 90 degrees is 0. Now consider triangle OPR. Applying triangle law of vector addition, you get vector RP is equal to vector R minus vector A. Similarly, applying triangle law of vector addition to triangle ORS, you get vector RS is equal to vector B minus vector A. Now applying triangle law of vector addition to triangle ORT, you get vector RT is equal to vector C minus vector A. Let us substitute values of vectors RP, RS and RT in terms of position vectors in the equation vector RP dot vector RS cross vector RT is equal to 0, you get vector R minus vector A whole dot vector B minus vector A cross vector C minus vector A whole is equal to 0. This equation represents the equation of the plane passing through three non-collinear points in vector form. Now, to obtain the Cartesian equation of the plane, let us assume that the coordinates of point R are x1, y1, z1, point S are x2, y2, z2, point T are x3, y3, z3, and point P are x, y, z. Vector RP can be represented in the component form as x minus x1 I cap plus y minus y1 j cap plus z minus z1 k cap. Similarly, vector RS can be represented in the component form as x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap, and vector RT can be represented as x3 minus x1 I cap plus y3 minus y1 j cap plus z3 minus z1 k cap. Cross product of vectors RS and RT is the value of the determinant in which elements of the first row are I cap, j cap, and k cap. Elements of second row are the scalar components of the vector RS, and the third row consists of the scalar components of vector RT. Now, the dot product of vectors RP and RS cross RT is given by the determinant in which elements of first row are x minus x1, y minus y1, z minus z1. Elements of second row are x2 minus x1, y2 minus y1, z2 minus z1. Elements of third row are x3 minus x1, y3 minus y1, z3 minus z1. On substituting the value of dot product of vectors RP and RS cross RT in the vector equation, vector RP dot vector RS cross vector RT is equal to 0, you get the equation of the plane in Cartesian form. In this module, you have learnt that vector equation of a plane that contains three non-collinear points with position vectors A, B, and C is dot product of vectors R minus vector A and vector B minus vector A cross vector C minus vector A is equal to 0. Cartesian equation of a plane passing through three non-collinear points x1, y1, z1, x2, y2, z2, and x3, y3, z3 is determinant in which elements of first row are x minus x1, y minus y1, z minus z1. Elements of second row are x2 minus x1, y2 minus y1, z2 minus z1. Elements of third row are x3 minus x1, y3 minus y1, z3 minus z1 is equal to 0.